So we are ready to start our lunch presentation. So I have here with me on the podium Dr. Volker Quetschke. He received his PhD in physics from Leibniz University in Hanover, Germany. His thesis was on noise correlations in neodymium-doped yttrium aluminum garnet. How did I do? Okay. Laser systems. He also worked on the laser system for GO600, which was a gravitational wave detector located near Hanover. He was a postdoc and later research assistant professor at the University of Florida in Gainesville, where his main work area was on the development and realization of the input optics for enhanced and advanced LIGO, which is the Laser Interferometer Gravitational Wave Observatory. Dr. Quetschke is now an associate professor at the University of Texas, Rio Grande Valley, Valley in Brownsville, working on advanced LIGO input optics, photon calibrators, and stabilization of 1550 nanometer coupled laser systems. He is a member of the LIGO scientific collaboration and chair of its lasers and auxiliary optics working group, guiding the development of lasers and optic techniques for further gravitational wave detectors. He was part of the team that detected gravitational waves for the first time late last year, just 100 years after Einstein first predicted them, for which he is a co-recipient of the Breakthrough Prize in Fundamental Physics and the 2016 Gruber Cosmology Prize. Dr. Quetschke is the author of more than 130 refereed publications and holds 2 patents. Dr. Quetschke, I warmly welcome you to the symposium. The stage is yours.
Thanks. Thank you all very much for the invitation. I'm happy to present today the Advanced LIGO Gravitational Wave Detector, and basically I really need to stress I'm one of 1,000 other people, and a lot of them worked on the hardware and even more worked on the theories behind that. And this whole work was mainly funded and made possible by the National Science Foundation. So with that out of the way, what's actually the plan for today? So I'll report about, well, obviously the first direct detection of gravitational waves. And to put that into perspective, I'll show you a little bit or give you a primer on gravitational waves. So basically, what is fundamentally behind them? Where do they come out? How do they come out of Einstein's general theory of relativity? And after that, because we're all more interested, I guess, in how the stuff works and how to build stuff, is how actually can we measure them? And then after giving you kind of an overview about technically it's supposed to work, then I'll actually show you a couple pretty pictures about how the LIGO detectors actually look at the current state and how they manage to detect that. And if I have time left, I'll give you a little bit overview about future plans. So with no further ado, on February 11th, it was announced by the LIGO scientific collaboration that we had found a gravitational wave. Obviously, the detection itself was not February 10th, but it took some time to verify that and write the paper and get everything peer-reviewed and make sure everything's nice and correct. But basically, so from the New York Times to the Brownsville Herald, the tiny little newspaper we have in our town, and Obama congratulating us. It was kind of, it made the news cycle. It made, I think, several 24 hours news cycles before it subsided down. In our fast-paced time, that's kind of something. Physics never gets to do this normally. So I was very happy about that. Oh yeah, and basically this is what the scientist in us craves the most. We have the physical review later. Basically, we have the detection paper about how the signal looked. Okay, come on. So what is the fuss about general relativity and gravitational waves? So as Ian already mentioned, after just 100 years of working on this, we found the last missing bit. So the theory of general relativity basically predicts that it's a geometric theory of gravity, and basically gravitational waves come from the curved space-time. Sounds complicated. I'll show you a simulation in a second. And some other things that are predicted by general relativity is, well, black holes, everyone talks about black holes nowadays, but it took the astronomers and the cosmologists quite some time to actually wrap their head around that there's something that has more or less infinite mass on a tiny little space. But it's part of the general relativity. So the last missing prediction of the general relativity was, well, if these gravitational waves are there, can we actually directly observe them? And there's compelling evidence that they exist because already, I should have written down the year, but something like 20 years ago, Taylor and Hulse actually got the Nobel Prize for finding that the binary neutron star system PSR 1913 and 16 is spinning up, and by doing all the math, they found that is losing energy, and the lost energy in their star system, or in that double neutron star system, is more or less on point of showing exactly the predicted amount of what it should lose if the general relativity theory is right. So it's a little small here, but basically the straight line is the theoretical prediction, and the red dots are the measurements over time. And so they actually kept measuring afterwards, and the prediction basically is dead on. But this is a passive measurement. This is kind of, you say, well, there is an emission going on somehow, and there's energy lost to the system according to gravitational waves. So it must be gravitational waves, but no one has seen them yet. So a little bit of an overview to give you an idea how gravitational waves can be conceived. So I promise I have of the order 3 formulas in this whole presentation. So what actually happens is, if you think of our 3-dimensional space, if you project it kind of into a 2-dimensional space, you can assign the warping of the space-time by larger masses. This is supposedly the sun, and this is the Earth, kind of putting dents in the fabric of space. And Einstein's theory is a completely gravitational, completely geometric theory. So if you actually think about the Earth being here, you could think of, if this would be a stretched piece of fabric, and this would be a marble, and you give your marble a little push, the marble would kind of run around in that funnel. It's not a perfect analogy, but it's one that works actually. So by just denting the space-time, gravity is the force that represents to following the geometry of space and basically following these lines. Okay, so this is a static picture. And I said, well, if you give the Earth a push, it rolls around. Okay, so if something like this moves on a surface, and if this would be a water surface, and you basically move something on the surface of water, what you generate is ripples. You just generate waves. And the same is more or less happening if you move very heavy masses around. So the coming simulation, can you please start the simulation? Down, yeah. So this shows two black holes circling around each other. And as we zoom closer, you actually see the space-time here is curved into each other. And so now they actually circle around each other. And if you would sit kind of somewhere outside of the screen and would measure the height of this fabric, you would actually see it starts to create ripples, just like ripples in a pond when you throw in a stone. And then, because energy is lost, these two stars, neutron stars, get closer and closer, as you can see here in your simulation. It kind of will end in a cataclysmic event where they kind of hit each other and merge together. So now the simulation is slowing down, and what you can see is probably very faint in the background, but what you see is, instead of having a nice sinusoidal speeding up curve, what actually happens is you kind of get this like a chirp, getting faster frequencies and then merging together for one object. So this is what the theory said. Around 10 years ago, some scientists actually at my institution and also separately at NASA Goddard finalized the theoretical calculations to actually simulate a binary neutron star merger. And so they had a very good idea how this will look. no one had ever seen it before. So what would you actually need to do to see it? Because as I said, this creates ripples in the fabric of space. So if you know, and these are the three formulas I was mentioning, if you actually look into general relativity and see what actually happens if you are outside here and you have this neutron star, double neutron star system, you actually generate something that's called a strain that is depending on a lot of orbital parameters and distances. I'll get to those on the next slide. But basically, you get a formula about what you can observe if this happens at a distance from you and you are standing here on Earth or in orbit somewhere. So, sorry. And what is the observable effect? This H is a strain. Basically, the strain is deforming one dimension by elongating it and pulling the other one. So can you please start this video too? So this is the video of kind of a gravitational wave coming here from the right side and then coming through. It's a continuous gravitational wave keeping to oscillate. And what you would actually see is if you start with a round ring here, the gravitational wave would stretch this in both directions. That's kind of going wee, wee. Okay, so obviously this effect is huge. If we would experience a huge effect like this, we would feel wobbly all the time because of cosmic occurrences. Here's your formulas, not new formulas again. So now we actually have to think about how big is this H, actually, this strain. And so now the theory part is, if we want to expect an H of 10 to the minus 21, and this is not completely arbitrary chosen, but this is kind of the value we want to observe of a relative length change of 10 to the minus 21. We actually need two objects of roughly 1 solar mass. That fits, that's usually neutron stars. They should be in orbit around each other at around 400 Hertz. What is kind of incredible. Let's think about it. This is two suns, like the one somewhere up there, circling around each other 400 times a second. Pretty cosmic, I would say. We are away 10 megaparsec from that event. Yeah, you want to be a little bit away from that because that's a little violent. And, oh yeah, this capital R is the distance of the two objects from each other. So if you have these two neutron stars 20 kilometers away, oscillating, circulating around each other at a certain safe distance, you would actually get on Earth this relative length change of 10 times 10 to the minus 21. Pretty weak, I would say. On the other hand, this is what happened last September. The detector, I'm going to show you a little later, kind of got a signal that looked like this. So we were looking, normally it's supposed to be flat or just noisy. But what we got is we got this chirp, just like my simulation that I showed you before predicted. So there was this. And, well, this is why I kind of choose the 10 to the minus 21, because we have a strain here at the peak of the signal of roughly 10 to the minus 21. And so there was something like this. So now, what does actually 10 to the minus 21 mean? Well, if you have a 4,000 meter long detector, however you build it, again, I'll get to that, this corresponds to an actual length change. Don't tell that to an astrophysicist. This is experimentalist slang. It's a fluctuation in the space-time metric. But the observable effect is as if the length would change by 10 to the minus, 4 times 10 to the minus 18 meters. And funnily enough, it kind of is a signal that is in the audio range, because here's the time, this is a time series. So you actually have oscillations of a couple milliseconds. So I hope this works. And if our team over there got the audio working, and once you start that, we'll actually hear the gravitational wave. Let's see. Well, didn't work, because there's a high frequency part at the end that is filtered out by this audio system here. I'm sorry for that. I can show it to you on my computer later, or actually you can listen to it on my computer later. What you would actually hear is you would hear a chirp at the end, and wheek, wheek. Anyway, so here's a spectrogram. We're all scientists here. We know what a spectrogram looks like. So basically, here's your frequency components, and here's the time signal over time. So on top of this rumbling noise you actually hear, here's a chirp at the end. All right, so some perspective. I just throw 4 times 10 to the minus 18 at you. How big is that? So 1 meter? Human hair? Well, you have some. Wavelengths of light, I just use 1 micron. Usually it's a little shorter, but 1 micron is actually the wavelengths we use in the detector. Then from the wavelengths, you actually need to go 6 orders of magnitude smaller to have an atom diameter. And then you need to go 5 orders of magnitude smaller to have a proton diameter. And then you need to actually go nearly 3 orders of magnitude smaller after you reach the proton diameter to go to the gravitational wave amplitude. And you might now say this guy is nuts because he just predicted, or he just said you can measure changes that are smaller than a proton diameter. Yes, we can. I'll get to that. And on another note is if you actually take this relative length change of 10 to the minus 21 of the strain, if you think about that, our sun is roughly 150 billion kilometers, 150 billion meters away, and you multiply this with the relative change, that actually means the distance of Earth and Sun when the gravitational wave came through had a change of roughly 1.5 times 10 to the minus 10 meter. That's a moderately sized atom. All right. So how do you actually measure this insane small change? So what you do is you do some interferometry. Animation, please. So basically what we have here is this is how the detector will look. It is a Michelson interferometer at its heart. And once the animation starts to zoom in there, you will actually see the amplitude of the carrier field. In this case, the carrier field is at about 100 terahertz, but still it has a wavelength. The wavelength is about 1 micrometer. And if you just have the distance between the mirrors just right, the amplitudes cancel each other and you have the dark port here. So now a gravitational wave comes through, meaning the end of the two, or the lengths of the 2 arms change slightly, and what you actually see is going from dark to bright changes actually the signal here at the dark port. And it's not super sensitive, but you already made the first 6 orders of magnitude, because your yardstick that you're using here is the wavelength of the light that you're using. So from just trying to measure something, you already have an inherent sensitivity from dark to bright of lambda over 2. So that's half a micrometer already that you kind of get for free. But you all know we can do much better than just look at, say, this is dark and this is bright. So we just now need to put the distance between dark and bright and kind of cut it into 10 to the 12 pieces, and then we have the sensitivity that we need. All right. So the basics. You all know this. I'm going to slide forward. So here's this intensity curve that we just saw. So basically, we just sit ourselves here, and if you look at the output response, you take the derivative. Oops, I put a couple more formulas there. My bad. But anyway, so basically, the change of the output light here on the photodiode changes with the phase, and the phase is proportional to the length, to the differential length of the arms. So what you actually get is you kind of get the intensity change at the output that is proportional to the differential length change of the arms. And also what you see is it also multiplies with the power. You just assume you put yourself kind of on the dark spot, and then you put an insane amount of light in there, and you get a sensitivity that is proportional to the light used. Another thing is everyone here is familiar with shot noise. You also need to beat the shot noise. So therefore, you better make your P decently sized. Okay, so what's next? The strain that is predicted, the H, is a relative length change. And obviously it's delta L over L. So if you then look at the change, at your phase change over changes of H, you see immediately, well, the longer you make your baseline, the easier it gets to measure those changes. I mean, these 10 to the minus 18 that I'm throwing around is based on 4 kilometers length. If you would build a 1,000,000 kilometer long detector, it would get easier. So, but that's kind of one thing. Keep in mind, large L helps. Obviously, we're still at 10 to the minus 6, roughly, from the yardstick. And now we kind of need to improve the techniques and get it a little better. And one thing you can actually do is, instead of just using the regular arm length, where you kind of probe this phase change by changing the length, the total length over lambda, by optically enhancing the effect in there by basically creating an optical cavity in there. And for those of you that don't really know what happens, if you actually reflect light back of a cavity and you change your light frequency or your wavelengths over the resonance of the cavity, you actually get a cavity response like a dip. But what's more interesting is the reflected light gains phase. And what happens is, if you make the cavity response fairly narrow, instead of exploring this 2 pi phase shift when you change the lengths of the interferometer arms by 1 lambda, you actually move this 2 pi phase shift over the resonance width of the cavity. So depending on how much gain you dare to put in there, you actually get this as a factor on top of the sensitivity. For practical purposes, you end up with not much more than 100 because we're dealing with a huge instrument, but already there's a factor of 100 that you can just bank. The next thing is, as I said, we're going to keep this in the dark, and that means for energy consumptions, energy needs to go somewhere, and we build good detectors that don't absorb, meaning all the light goes back to the laser. Not only is that bad for the laser system, but it's wasted. And so basically what you can see is you treat this whole interferometer as a complex mirror, meaning a complex response function of the reflectivity, and then you just put at the right distance another mirror right in front of it, and you build a cavity with the whole interferometer around. And as I said, more light is better. So by this, we call this power recycling. You actually get another factor of free light power by recycling the light power. So you get another factor of, depending how much you dare, but 100 is yet again a good estimate for this. So now we have the Fabry-Perot factor, the power recycling factor, and the last trick we can use is, if you think about what the gravitational wave actually is, it changes the length of the arms, so it kind of transfers light from the carrier into sidebands. Sidebands are just regular frequencies, or basically they are Fourier frequencies. So if you now build another cavity, I know we love cavities, that actually enhances the signal strength of the leaking out signal and sends it back, and now this is not resonant at the full interferometer anymore, only here in my green indicated pieces, you still get a cavity that enhances the signal sidebands. Giving you the signal recycling gain is a little iffy because it really depends on the line width of the cavity. But you can get a factor of a few, maybe up to a 10 out of this. So this is kind of the last trick that was installed and implemented only in the latest version of LIGO and the current advanced LIGO system. All right, so assume we have 1 million here, so we only need to actually measure our line width now to a factor of 1 million. Sounds doable. I mean, that's a signal to noise that we can handle. But are there any other problems? So I'm talking about the laser system and a lot of optics hanging around somewhere. So you can just imagine putting them on the table and try to measure this, and it will just not work. Because the problem you will face is you have your test masses, what we call the mirrors, and if there's gas in there, just the fluctuations of the gas by having vibrations going through the gas change the arm lengths much, much more than you will ever able to measure. So you need to get rid of that. If the laser fluctuates either in amplitude or in frequency, or in wavelengths for that matter, that looks like as if the arm lengths would change. So you need to make sure, at least on the specification that you want to see something in the end, your laser better doesn't change frequencies and intensities. And that actually translates into fairly low, we usually do spectral densities, but if you want to speak line width for this, the laser line width is of the order millihertz out of 100 terahertz. And the intensity fluctuations, that's basically trying to beat shot noise, we are with advanced LIGO at a few times 10 to the minus 9 relative. So we need to detect about 100 milliwatts to get to that level and then stabilize that. But that's for later. Oh, yeah, the next problem is obviously seismic noise. Again, if you put the mirrors on the table, you just feel the earth shaking and not the gravitational wave coming by. And then once we're to the right level, you'll actually see that the Brownian noise, the thermal noise of the substrates itself is actually dominating the effect that you're seeing. So basically just by having the Brownian motion of the atoms and molecules, you kind of lose there. So this is actually kind of, and the next class of noises is quantum noise level. And as I said before, shot noise is a quantum noise level, and radiation pressure is kind of, the problem there is the coupling of the intensity pressing on this mirror, trying to move the change, trying to move the position. So, and it's kind of a trade-off. Shot noise goes down if you increase the power, but if you increase the power, the pressure on the surface actually grows up, and therefore every fluctuation that you put into a laser beam will actually change the force that's acting on this mirror, and therefore try to push the position. Oh yeah, and why is it trying to push the position? Because they are not bolted down. Because as you will see in a second, all our mirrors are free swinging pendulums with some location control. All right, so we kind of need to know where this is going, and this is a noise plot for the advanced LIGO design. And so basically we made sure whatever we're doing here, the red curve is what we can't beat at the moment. That's the thermal noise of the substrates. I mean, short of cooling everything down, there's coating research going on, but this is, it has been built, so this is what's out there. Can't really change that now. And what you see here, the suspension thermal noise is the blue curve. That's basically, the Earth is shaking, the stronger, the smaller the frequency is. And this just falls with 1 over, I think, f to the 8th, because we have multiple pendulum stages to filter this out. And basically here at the end, it actually comes back because all our cavities have poles, and the pole frequencies are of the order of kilohertz. So the optical frequency is actually limiting the sensitivity for higher frequencies. But here, as you can see, in this middle range, in the sweet spot area between 50 hertz and roughly a kilohertz, we are less than 10 to the minus 23, theoretically. Okay, these are the design specs. I talked about those already. So how does it look? I mean, I showed you the plot about the sensitivity when we did the detection last September. So first I should say the previous best is the enhanced LIGO detector. That also took a couple of years to get going, 5 years back. And so we're not that much better than that, than we were before, but we are actually significantly better. So kind of factor of 3 or so, we're, well, 2.5, we're better. And the blue curve is the design spec I showed you. We're not there yet. Commissioning is still going on. But this was kind of the sensitivity of the observing run. And you see kind of 2 reddish curves. One is the Hanford detector, and the other one is the Livingston detector. It's 2 detectors. Both need to see something, but they are kind of fairly close. So once you actually say you take measurements, this is how your signal usually looks if you take measurements with or without a signal. So inside this is supposedly this chirp waveform I showed you. And advanced data analysis techniques can actually pull them out. And you should be, here you're actually having the signal. Here's a signal to noise with this matched filtering. It actually sticks out a little bit. This is the design what we are working with. But now, sometimes the universe is really nice to you. For this very first detection, the detected signal actually had a signal to noise of 25, and this is why I could show you the time series with the actual oscillation going on and the nice chirp that was visible. We were discussing actually in the collaboration, who will ever believe us and how long will it take, how many measurements do we need to take of measurements that look like the one that's covered there, because it really comes only out in the numerical treatment of the signals. But we were lucky, all good. So we really saw something that is so strong that it peaked out of everything. There was actually someone sitting in the control room the day it happened that got a small red light, and he looked at the time series and said, whoa, well, we need to actually call the people and they need to get started with the analysis right away. Normally you find stuff like this after a couple of months, basically chomping on the data, and then someone finds something. So this was a really, really good detection. Okay, so why did it 100 years? Should be obvious by now. I mean, so we need a very sensitive instrument, and it's a big task that cannot really be tackled alone. So who's working on this? LIGO scientific collaboration is something like 1,000+ members coming from more than 80 institutions, and I hope the count is still right. It used to be 16 countries all over the place. I'm there. So, well, the obligatory logo thing, so it's a lot of people involved there. But where are they actually? So the detectors are one down in Livingston, so not too far away from us, and the other one is up in Hanford. So this is Washington State, this is Louisiana. They're fairly big. 4 kilometers is 2.5 miles. So you need to actually get some real estate. We have some interesting tenants living around. And you might wonder, because I didn't tell you why do I actually need, or why do we need 2 detectors? For detection, not for observing, but even for detection, you need coincidence, because the noise level, you're speaking about fluctuations that are so small that you need a convincing measurement that this is real. And the best way to convince yourself is you take 2 independent measurements. They are not related except by internet, where you take the measurements and you have 2 places on Earth that measure the same thing individually. And if you actually see the same signal creeping up at both detectors, you can be fairly sure it is independent from each other. And the next thing is, light takes about 10 milliseconds to go from one detector to the next. So by time of flight correlation, you can actually find the direction where the signal is coming from. I didn't go to source polarization. Actually, gravitational waves can have a polarization, but I'm going to skip that. So the orientation is chosen to optimize sensitivity towards that. Anyway, so advanced LIGO, because this is what the aLIGO stands for, is kind of the 3rd installment of the detector. In 1997, we started building the first one. That was briefly before I became part of the collaboration, but only by 1 year or so. And over the years, it kind of extended its reach. Hard to say, but the original reach, this is a picture of the local supercluster, and there's a small bubble in here that was the original sensitivity, and the yellow one is actually the reach of the current detector with something like around 80 megaparsecs sensitivity to standardized neutron star coalescence. So that basically, that's the fancy way for the astronomers to say we pick the most probable astronomic event to happen, and how far away can we see this most probable event. Okay, so it just doesn't look like much, but basically you're 10 times more sensitive thing, or you're 10 times, being 10 times more sensitive than the original one gives you 1,000 times larger volume in space where these waves can come from. So, and it's not, I mean, you need cosmic events. There's not 2 neutron stars annihilating each other all the time, or black holes hitting each other. So we would also be sensitive to supernovas, but even that stuff doesn't happen every second. So we kind of, the larger the area you observe, the better. So another thing is we had significant improvements over the years. We needed to actually suppress the seismic noise, and going from just purely passive suspensions that I will show you, there's now actually active feed-forward suspension where the whole vacuum chamber is suspended from the outside with a hydraulic system that counteracts the Earth movement. A lot of work has been done on the Brownian noise. I mean, I'll show you the mirrors. They're about this size, and they are now fused silica complete, meaning there's actually fibers from fused silica welded, melted to the big optics so that you avoid the dissipation effects of having two different materials combining each other. And obviously quantum noise, so what the easiest way for us to do is beef up the laser system. Here it says 120 watts. That's just because we lose nearly 40% by going into the system. It starts with a 200 watt system. Okay, so what does it help? Basically, this is the original curve. This is the new design curve. Everything has gotten better. And now the fun part starts. Now is where the engineering really starts. What I gave you so far is a high-level overview. So I showed you this interferometer, and there's a laser, there's a photodiode, and a couple mirrors. Then it's not that easy. You start with a laser system. You need to actually clean up the transverse electromagnetic field. We do that with another cavity. We need to actually do the alignment into the cavity. We need to match the cavity, the power recycling cavity, to the complex mirror of the whole system. We need to match the signal recycling cover with the whole system. You see there's double plates. There's one mirror here and a small mirror there. That's because you need compensation plates. Because if you have the laser beam in there, it gets hot. You create thermal lenses. So you need active, controllable thermal compensation systems where you can act on not your test optic, because that would be bad. So you put another transparent optic in there so that you do. So this is kind of second order approximation. What you need to do is, and then you start putting it into vacuum chambers. And I hope the next picture is coming up soon. So this is the preliminary overview. And then you actually go to SolidWorks drawings of every individual item in the vacuum system. And the LIGO system has, or the LIGO project has a complete SolidWorks drawing of all the detector and optical surfaces and all the elements in the mechanical and the optical path, so that we know if we put new elements or new stuff in the vacuum system, we're not accidentally hitting something, and so that we can do scattering calculations if light comes back. Anyway, so let's actually look at the hardware in general. Yeah, we were lucky. So you see here, these are the vacuum tubes. They are 1.2 meters in diameter, and they are protected by a concrete shell, and that is a good idea. One of the detectors is at the Hanford Reservation in Washington State, and because that's federal property, they have something that's called the Hanford Patrol, and that guy was cruising around, and there's a berm, and so kind of was driving over it. Well, what can happen? He's driving a Range Rover or something. Well, he got stopped by the tube. Also, this is more in Louisiana, cover the tube against hunter's bullets. Hunting is very common in Louisiana, so it also helps to have a concrete shell. Okay, how big is this? I should have picked a picture with people standing around. So these are the ham chambers, meaning that's our experimental chambers where we can work in. And from the ground to the top flange here is about 6 feet. So the whole thing is about 15 feet high or so. And it's all in a big, nice construction hall. It's a very good vacuum system. So because we really need to evacuate it down to very low pressures, and that means it's kind of 10 to the minus 10 millibar, at least for hydrogen pressures. The most important part to get out of there is anything that can do electrochemistry. Because if you have actually any carbon molecules or carbon-based molecules in there that go to the optical surfaces, and you have a megawatt light field shining on that, what will actually happen is whatever is in the coatings will get out of the coatings, will do some chemistry, and the next moment you actually have a small hole in your coating, and after that you actually have a big hole. So you don't really want to do that. But here is the reason why I always say we have this pendulum. So all our optics are free test masses. Well, the perfect thing would be go into space, put everything in orbit, and don't touch it. Can't really do that. But the next best thing is to just hang it from a thread. Because that way, it's only constrained in the z direction. X and y can still move. And the next good thing about doing this is it also forms a pendulum that has a resonance frequency, or a corner frequency for that matter. And if you actually do that, everything that's higher than the corner frequency gets suppressed. So this is good for GR, and also good to reduce the noise. Okay, so again, this was the conceptual point. Everything needs to work into vacuum, and so all the mirrors, everything that I showed you in my high-level drawing, all of them are kind of in steel or aluminum constructions and are suspended. And one thing I didn't mention is you can't just hang it, you need to control it while it's hanging. So for the not so sensitive optics, there's actually something that we call shadow sensors. That's coil actuators. They're small magnets glued on the back of the mirrors. And this is not the real sensitive mirrors. This is everything else. And there's an LED shining from one side across to the other one. And there's the magnet itself that's glued on there is acting kind of as a flag blocking the photodiode. So if the photodiode is blocked by the optic moving in a little bit, it blocks the light. And you have a combined actuator, because if you then wrap a coil around that and put a little bit of current in there, you can actually either pull the magnet further in or push the magnet out. So each of them is what we call locally controlled and damped. So what you also don't want is you just give your pendulum a swing and it will just swing forever. One thing is what we want is very high Qs, and that's terrible if you actually want to wait until it subsides. There's no air to damp it, so it will just swing more or less forever. So you need to kind of measure those and make sure that your actuation frequencies are always out of the measurement band, because last thing you want to do is suppress everything you want to measure. Anyway, so everything's suspended with pendulums. Here's the big guys. These are the pendulums for the actual sensitive elements, and that's basically the end mirrors of the interferometer. Everything else is kind of steering and beam preparation. But here, what you actually see here is this mirror down here, or the one on the other side, so not the one with the funky rings on it, but the one that you can't see on the other side, is the actual really, really sensitive test mass. So you have this 4-stage pendulum giving you 8 orders of suppression. A couple of them are actually vertical suppression by using springs like this. And then the problem there is, okay, now we have a very good suspended pendulum that is not moving anymore. But now you actually need to change the length a little bit to adjust it to find the right wavelengths to resonate the cavity. How would you actually do that? What you see here is an electrostatic actuator, meaning by putting a high voltage on there, you can actually suck the other optic towards it, because it's a dielectric essentially. It's glass, it's fused silica. And so by just controlling the strength of the voltage, you can actually pull it a little more or a little less. And again, you only want to do that at frequencies where you don't disturb. But there's no actual acting or touching the lower test mass, because that's what I call this monolithic test mass. So basically, I hope I have, no, I don't. Unfortunately, I don't have a nicer picture for that, but down here, these wires here are not actually wires. Those are fused silica threads that are welded to the big optic. And they weigh 40 kilograms. They're about yay big. So it's kind of sensitive to touch. But also the small ones are actually all suspended. Let's skip forward. My friends in Hanover, this is actually where I came from and where I started working on the frequency stabilization in the beginning. They provided the laser system. So 200 watt is, as far as laser systems go, nothing special. But if you have a 200 watt laser system that has a line width of a couple millihertz, that's more the special type that you get. So it was absolutely completely built for this project. There's only 4 of those systems, 3 for the LIGO detectors, and 1 is a prototype that is kept in Hanover at the institute that built this for reference. If something breaks or if they want to test something, that they can play with it without disturbing anything that's important. Oh yeah, here are the pictures. So basically, I showed you these 3 levels of sophistication. Here, this is part of the input optics and how crowded the tables are inside. The only thing that is kind of not real is the red and blue tubes, red and green tubes are actually representations of the light fields. So we kind of abuse SolidWorks as a 3D designing tool to introduce another material that is essentially light, so that we can then do intersection measurements and see if something is actually clipping the beam. And you might think, you just see it. If you stick the stuff in there, you know nothing will actually hit something, or you don't really have problems there. But having these 3D models really helps you out. If your beam line is 4 kilometers long, you have of the order 10 of such vacuum tanks, and you really want to make sure that what you're doing does not impede the performance of the system. So kudos to our engineers. That's a huge feat. And I think they needed to keep buying bigger computers to keep this actually running in the simulation, because it's insane. And this is only kind of the input power part, or the input optics part, where I worked on. So the level is roughly staying the same, but you have beam conditioning for the light coming out of the interferometer, and you have the measurement or diagnostic outputs, and everywhere you need to actually make sure you get the light out of the vacuum system. You must not hit any non-isolated surfaces, because if you do, you could backscatter back into the instrument from a surface that is not isolated, and that means you actually couple ground motion, ground vibration back into the system. You might say, yeah, but the coupling is only 10 to the minus 10. Yes, it's 10 to the minus 10, and we don't want that. So, okay, so on the PSL, so basically the laser system I showed you, the edge is down here. So this is kind of the easy part, but it's a little bit crowded. But basically, all the light on the outside is done there with a tiny little laser beam, 200 watts. And then what you don't see is it goes from here into the vacuum system, and from there everything is kind of hard to touch. What is kind of a nice feat to remember is you kind of get this laser system, and you need to match the parameters of the light field to the parameters of the internal system. And this happens with 97% accuracy. That means the incoming beam is actually so pure that you can couple it to a theoretical cavity. And also what happens is we don't mess the beam up anywhere to actually degrade. So 79% of the light, basically at the bottom of the periscope, is getting into the mode cleaner that makes sure there's no transversal vibration on the beam anymore, and then goes on to the interferometer. Okay. This is one of the earlier prototypes. Looks a little ugly, but basically I'd like to show that to you, because you might think, well, 200 watt, not that hard. Let's just go online and buy a Faraday isolator. What is that? That's basically an optical element that prevents light going back to the laser system, because they don't like that. If you shine light back to the laser system, it actually becomes unstable, at least these types of laser systems. So, but the problem then is, if you have a 200 watt laser beam, you realize very fast, I can't buy this online. I actually can't buy that from anyone. And so this was developed in-house, and this was the first prototype. And you can't really see that, but this is the final design. The magnetic field inside there is 1.5 Tesla around the beam, done with permanent magnets, and the field is actually going along the beam axis. So you need a kind of pie-shaped structure that you then rotate around with permanent magnets. I'm happy to show you a picture later, but I'm just showing this because I worked on that, and I want to show a little bit of the stuff that I did. Anyway, so here's the early installation phase. There's not much on the table yet, but you see already we're kind of not touching the table. The surface here is a stainless steel surface of the vacuum chamber, not of the vacuum chamber, of the optical table that is vibration isolated in the chamber. And the problem there being the vibration isolation, you actually touch that like this, and the whole thing does this, because it is sitting on springs. So we're actually leaning here on the crossbar on the outside, and everything else you do on the table is you basically just touch what you want to touch and then leave it be and get out of there. Everything needs to be done in clean room conditions, and there's actually an excess pressure in there, so that basically you have wind blowing towards you, so that even the openings for the eyes and where the glasses are actually don't let any particulate fall into the chambers. Just like semiconductor production. Maybe not as stringent, but pretty strong. And this is a 3D view of very bad one of the chamber. So basically this is roughly 10 feet in diameter, and all in there is shiny either glass, aluminum, stainless steel, and a little bit of Kapton. So the gas load is basically highly restricted. If you want to bring something in there that is not glass or aluminum or steel, you actually need to ask systems for permission, and they might weigh it and ask you to cut it down or make it smaller. The test masses. So when they actually started building the first detectors, they found no one could produce test masses that were polished good enough for this. So one thing I haven't told you so far is how can you actually measure something that is smaller than a proton diameter? What actually the answer to that is averaging. So if you think about that, you have 10 to the 23 molecules in a mole and distribute that over a surface, you basically have a lot of elements making up a surface, but the distance from each other to the other one is fixed, so that then on average you actually get a surface that gives you a reference surface for the reflected light. So this is the only way you can actually get something that has basically a smaller distance than the structure of the inner makings of a nucleus. So, but that also requires that that surface over there is very, very flat. So it's not flat to this 10 to the minus 18, because again, of the averaging, on the other hand, if it actually would have ripples, the beam would not look very nice anymore if you propagate it for 4 kilometers. So you have to have very, very good surfaces and coatings, and actually the optical round trip loss, and it's still a little bit on the high side of the current cavities as they were put in advanced LIGO, is actually losing something like 75 ppm. That limits also this gain factor that I said for the arm cavities. You can't just say, let's make the gain factor 1,000,000, because 1,000,000 wouldn't work with that loss. Anyway, so from there, you basically need to make sure you get the best of the best. And then you kind of measure the surface, you polish it, and you get interferograms of the surfaces. And here, this is basically in nanometers, and you have something like, from the red spots to the blue spots, you have something like roughly 2 nanometer surface impurities, with wavelengths being that we're using about 1 micrometer. You speak of about lambda over 50, a little bit better, lambda over 50 over a surface that is 34 centimeters from here to here. And you see this donut structure here? That even is later corrected for. So technically speaking, you actually speak of fractions of a nanometer if you actually look at points that are close to each other. All right. Oh, I'm running out of time. So a couple other challenges is, because of these arm cavities, you're kind of sensitive to the position. You always want to stay on resonance to get your feedback loop going. But your feedback loop of the detuning of the length of the cavity is you need to be there plus minus 1 nanometer. And then the problem is you have this many cavities, at least 3 cavities for the inner interferometer that need to concurrently be locked. And I think I have a picture of that coming up. So yeah, basically these are the degrees of freedom. I'll just enable them all. So basically you have the interferometer that's itself, that's the blue, that's the Michelson, then you have the signal recycling cavity, that's one of the other blues, the power recycling that's out there, and you have 2 different arm cavities, and then the 2 lengths of both of the arm cavities, the differential lengths of those also need to be small to be on resonance. So that's a fun project for another group. And here's your multi-stage suspension. So basically hydraulics. I was not aware until they built that they could actually do precision hydraulics, meaning moving the whole vacuum chamber by fractions of a micrometer by using hydraulics, but they can. And what is basically the next thing we need to do is, so what I showed you is this and this. Geo 600 is on this, and I spent a fair amount of time there, but Geo 600 is only 600 meters in length. So it's what we call an advanced prototype. Everything that is new and someone needs to test under realistic conditions without disturbing the 2 big boys, we send it to Hanover and they can try. Virgo is another European detector that should have been running when we made the detection, and I think they're still hitting themselves that they were slipping in the timeline. Would have been nice to have them online because the spatial localization is much better with 3 detectors than with 2. But Virgo, on the other hand, will be up and running very, very, very soon. LIGO India is actually a US-sponsored project. It is planned / confirmed that the Indian government will pursue this. And the deal there basically is India will build vacuum system infrastructure buildings, but originally it was planned to have 3 detectors, 3 LIGO detectors, not in 3 locations, but in 2 locations, basically having 2 detectors in 1 location. That was more or less shelved and put into storage. So there is a full instrument waiting to be put into a vacuum system. So if you happen to have a big 2 times 4 kilometer vacuum system in your garage, that might be the place. And Kagra is in Japan and it's way on the way. They are tunneling through the mountains where the Grande detector was, and they will be up and running in about 2 years. Okay, planned to approve. So India is approved. That means the government moved ahead. When the next steps will actually happen is everyone's guess. So observing scenarios, to wrap this up, is we're kind of in the blue band of the sensitivity curve here. So this was kind of what was said, well, 2015. And that was our first observing run. And basically the prediction of binary neutron star detections was somewhere between 0.004 and 3. We got 1. Actually, technically we didn't get 1, we got 0, but we got a black hole detection, what is kind of falls into the same category. And the huge uncertainties are because space is big and the universe is even bigger. So it's really hard to make predictions about something where you don't really have good models for. So, but this basically, we were operating with a range of something like around 60 megaparsec for this neutron star detection. And here's the sky localization of the sources. Not necessarily the one for the detection I showed you, but if you take a hypothetical neutron star detection that is happening at there where the star is, the detectors would have shown you, well, it is somewhere there in the sky where the red streaks are. That's nothing you can call an observatory yet. That is, yeah, there's something there. But fast forward a couple of years with Virgo going and maybe LIGO India going. And what now happens is the sensitivity is much higher. And although you only have something like a factor of 4 or so from the original range where we started last year to then, the sky localization is actually very neat. So every one of these blue dots here, or blue circles, corresponds to what we saw as huge circles in the sky, just because of the many detectors. And the number of detections also is supposed to go up, especially now that we're beginning to get ideas on the lower boundaries. It's hard to do statistics with 1, but we're getting there. All right. Oh, I'm actually on time. So future improvements. So we need to have some detections, not only the 1. And we keep the R&D continuing because everything takes years. So LIGO, like it is at the moment, advanced LIGO will be continued to be commissioned and improved over the next coming years. And you can't really touch the detector at the moment. But R&D is going on for different wavelengths, for other high power materials, for improved control system theories to make better servo loops. So that's happening on the side. Even if advanced LIGO like this is reaching design sensitivity, we actually think about, we know a couple of techniques that can be implemented to give us another factor of 2, maybe 3 in sensitivity, like using squeezed light. And maybe if we don't want to change everything else, but we can convince to get someone to get larger test masses, that would also reduce the noise. So instead of having 40 kilograms, you make it bigger. It's a little problematic because you need to redesign part of your suspensions, but if you don't change everything, that is money-wise doable without redesigning everything. And then by 2035, or whoever put that number there, is it's just a guess. So basically, one idea would be going actually for longer distances. 4 kilometers is arbitrary. Technically, you can get a factor of 2 or 3 by just making the arms longer. 40 kilometers maybe a little bit excessive, but who says 10 kilometers is not possible? 10 kilometers is only 2.5 longer than what we have at the moment. So you're just limited by vacuum pumps and material. And so in summary, I'd like to say Advanced LIGO is complete as a project. First science run has been successfully completed, and now that I see that actually the first science run was not even declared a science run when it started. It was what we called an engineering run. That means everything was in place, and we just have it run for a couple of days, hours maybe, to see everything's fine, and let it sit there, and no one works on it, and then the signal came. And the difference between an engineering run and a science run is you have to have very, very precise documentation about the state of the detector. So what actually happens was that moment when there was the potential of a detection, everything that was still to be changed was immediately scrapped, and the detector was left alone. And the rest of the time was used to characterize the detector without changing anything. So we basically made the current engineering run into a science run by following protocol. What was, I think, a good idea. And so the next thing is, well, we continue to observe sensitivity, and the next real science run, or the other one was a real science run. The next science run is scheduled to start very soon. Next few months, and we want to actually transition from a detector who is there to detect gravitational waves to an observatory to do astrophysics with this. And again, I'd like to repeat this. I worked on this, but it's the work of many. So I'd like to thank the members of the LIGO Laboratory, the LIGO Science Collaboration, National Science Foundation, and David Shoemaker and David Wrightsey for providing a couple of the slides that I shamelessly borrowed from them. And with this, I thank you all for having me.
Very much for the talk, and this is a small token of our appreciation for you coming here. Thank you very much.
Thank you. I think we have questions here.
Questions?
Please go ahead.
Okay.
Yeah, go ahead, Ross.
Well, thank you for your talk, and congratulations on the detection. That's fantastic. This may be a dumb question, and it may contain circular logic, but ever since learning about this type of detector, I've been trying to figure out if you have a gravitational wave propagating through space, it's affecting masses that it's passing through or around. But isn't it also affecting the propagation of light in that same space-time? And so if so, how can we even detect it? Isn't it affecting the path of the laser as well?
The one constant part that actually is in there is the speed of light is constant, even in general relativity. So the gravitational waves affect what we call the metric. That's what I call space-time in here. And basically changes in the metric induce or that you have measurable changes in travel time. So I call that changes in length. That's not really true. What really changes is the travel time between the two mirrors changes. And that's the equivalent to changing the lengths if you assume that you don't change anything. So, but in reality, you're right. How can you measure the length change of something if your ruler changes length too? And you're right. But in this case, the ruler doesn't really change the length because the ruler is propagating with the speed of light. And in every frame of reference, confirmed by this, so far no one has proven that light deviates from traveling at the speed of light.
Thank you.
Thank you.
I have maybe a dummy question. So Fabry-Perot resonators has several resonating modes. Mm-hmm. Does it cause any problem here or not?
Oh, this basically, it's actually a good thing that it has several resonating modes because you don't really need to hit the absolute lengths exactly. You have every free spectral range, you get another mode that you can stabilize on. And as we are not really sensitive to the absolute lengths, more like length changes, it doesn't really matter much. Another thing with Fabry-Perot resonators, they actually have different transversal modes. So they have not only the TM00, the nice round mode, but all kinds of higher order modes. And there the trick is actually to design a cavity configuration that you have the highest losses for the higher the modes are. So you actually want to have it not degenerate. So you don't want a confocal cavity, for example, because we don't want higher order modes to resonate. We learned that the hard way because our first detector with the first power recycling cavity, because of the design, didn't allow for mode matching optics inside or between the beam splitter and the other power recycling mirror. It needed to have a confocal configuration. And that produced really horrible signals at the output, meaning horrible in the sense if you took a video camera and looked at the beam, you start with a nice round beam and you really get something that's totally terrible at the output. So this one here now, because it does inherent filtering, we basically have nice beams everywhere.
Thank you.
Thank you.
I missed one number. What is the speed of the gravitational wave?
It's propagating at the speed of light. So again, this kind of please ask the next astrophysicist for this because I'm not a specialist in general relativity, but it has the same properties as the propagation of the photon. Although gravitational waves are not propagated by photons, actually there is no closed theory for quantum. To find a quantum theory of gravitation is still the holy grail, so your ideas are appreciated.
So for the detector to detect the gravitational wave, so besides it detected the gravitational wave, does it verify other properties of the gravitational wave?
Say again, what does it?
So does the detector itself also reveal some other properties of the gravitational wave itself?
The only thing the detector can measure is basically the length changes, so what we call the strain, the H. You might actually say the detector is you measure all kinds of unwanted effects. You're right with that. So each detector alone is a very good seismometer, for example. I mean, on top of having the insulation, but still, I mean, if the ground shakes, it couples through. Each detector, and this is kind of one funny thing, is that we haven't seen yet, but we expect to see for the next generation. There's basically a gravity gradient noise because all masses attract each other. If you have heavy objects moving around in the lab, you might think that is an effect. Okay, lucky for us, the coupling constants, capital G, is not that large and we don't really see that. But we're actually getting into the regime that for the next generation of gravitational wave detectors, there might be the need for active compensation by placing masses, big chunks of concrete or so around the vacuum tanks to compensate for that.
So this recent measurement was two black holes colliding, but how do you distinguish black holes colliding from another astrophysical event?
That's actually a good question. So again, I would love to be the astrophysicist here, so I'll attempt an explanation. So what I showed you in this simulation before were actually two colliding black holes. And what they can do is they kind of can look at the amplitude form that they have and at the frequency. And from both of them, you get distinct frequencies and envelopes of the merger. And so no one knows, except from back simulating, what you need to actually get the signal form. So what I can say is the instrument measured this chirp-like form. There's actually some funny parts on that. There you see there's a beat node on the tail or on the end leading to the chirp. And that kind of gives you the alignment of the spins of the two black holes. So you have a lot of parameters, and then you stick them into your simulation, and you get something out of there. And the most probable parameters for these are actually 1.3 billion, no, 30 solar masses black holes at 1.3 billion kilometers, 1.3 billion light years away, so very far away. Again, so I built this stuff. So I think I'm approximately correct in my answer.
Great talk. I really enjoyed it. So I guess I was curious, since you didn't talk about this, was there anything particular about the geographic location of the detectors?
Try finding 2.5 by 2.5 mile big patches of land. So the one was, it's swampland in Louisiana, and the real estate price was low. And the other one is, I mentioned the Hanford Reservation. That's actually the nuclear testing facility that the US have up there in Washington State. And so it's in the middle of a desert with some nuclear testing facilities that are not active anymore, I must say, around. So, and both of them are fairly far apart. So they came into the kind of round of final 3 or 4 that they had. And then there were surely some incentives from the local governments to attract a big research project.
So I didn't see that you had background radiation included in your noise model.
Actually, in Hanford, we measure, or once in a while someone comes by and measures, and there is no elevated count. So we're good.
Thanks for a great talk. Very entertaining as well. One of your slides mentioned that there are there are spurious signals known of these chirp signals, but you didn't elaborate on that. And what are the sources of them? You know, do we believe that, you know, just getting correlated measurements from 2 sites has eliminated all the spurious signals, or are there cosmic spurious signals?
No, they are actually spurious artifacts from the detector. And so what that means is a glitch in the control electronics or a jump in laser power. And it's relatively unrealistic, or it's not very likely that those happen all the time at the same time at both detectors. But this is one of the reasons we need to do the correlations. And then to rule those out, we actually have, I mean, there's one signal that's this H. And then there's another 1,000 signals that give you all the other environmental channels. And so the first thing that we actually do to rule out the spurious signals is, if you see it in any of the other servo circuits, or you see it in environmental channels, we declare it spurious. Because, I mean, if the gravitational wave would couple to the EM detector, okay, yeah, well, no, that's a part of the spurious. And our data analysts usually call that glitches because they don't really know what it is.
Thanks.
We're a corporation over here with a balance sheet. So I'm just wondering what the future return on investment is predicted to be.
Yeah, I get these questions all the time. Well, the answer to this is, because it's not targeted research to improve, I don't know, signal to noise on Wi-Fi signals or faster computer chips or so, fundamental research only happens if it's state funded, and so therefore there's no thing, I would say, that came out of this at the moment that rivals Teflon. I mean, this is what the people always say for the space program. Hey, we paid, I don't know, $1 trillion and we got Teflon out of it. On the other hand, there's of the order of 1,000 scientists working on detailed programs that will probably make it into mainstream. I mean, I don't think anyone will use my modulators very soon, or this lasers will become mainstream use for everyone, but the stabilization techniques get out there. We actually do actively research control theory at the moment. a domain that was primarily engineering dominated by now, but because we have actually kind of 100 input, 100 output, multiple MIMO control systems that we actually want to optimize without waiting for the queues of a couple million that we have sometimes for the pendulums to subside down. So there's research going on that's hopefully showing more and more results. The optics research, well, what can I say? When we started building the instrument, meaning starting to excavate and starting to building the tubes in 1997, you couldn't buy the mirrors that you now can buy off the shelf. So basically there was a kickoff funding from LIGO for REO, forgot what the acronym stands for, it's a coating company, that now routinely sells you mirrors that have 1 ppm transmission and losses that are smaller than that. In 1997, you couldn't do that, but they got a couple $1 million to basically do pilot research for this. And it leached out. So as I said, I don't have the Teflon example, but there's a lot of small examples. We know a lot of things much better now than we knew when the project started.
Does this result kind of like definitively prove that plasma cosmology is completely wrong, and now the majority opinion is correct?
I think it's only a start, because it's the one proof that if you assume a black hole or 2 black holes with the parameters that we estimated with this are out there, you produce this signal. So what we need is more in the long run to do cosmology and parameter estimations, because once you get statistics, you can actually drill down on the physics behind this. So for now, I still keep this. This is a detection. We are still a little bit away from observation. But the astronomers are actually participating in this project by listening to our triggers. So every time the interferometer is running and we get a potential detection, basically there's some web page and some data channels that everyone can see where a flag goes up with estimated, if it's strong enough, estimated directions, so that telescopes can point into that direction. So was there something when the merger came up? Yes, a trigger was sent out and telescopes were pointed into, mind you, not a point in space, but a streak in space. And there was actually a gamma ray source that was close by-ish. But the resolution is really not close enough to say this is it or this is something else. Actually, the current opinion of the people that work on this more closely say, no, this is more like a coincidence. But the moment you get better accuracy, and we will get that once Virgo later this year comes online, the next detections with 3 detectors will actually get you a decent localization, not a streak anymore, but a spot in space, and then it's easier for the telescopes to look into that direction.
Last 2 questions.
I have one question, because you say the gravity wave traveling like light speed, right? So I'm imagining, how can the gravity traveling out from the heart of Earth, or maybe heart of the black hole? Because the graviton, right?
Yes,
photon.
but the thing is, think about it. The moment you leave the gravitational well, you actually kind of you're leaving the vicinity of the black hole while it's still there. And even while it's still there, the problem is while normally photons can't escape the black holes, but it's like, think of this analogy with throwing a stone in the pond. A ripple of the metric can still get out. Again, why is it exactly C? I took general relativity classes, but I haven't run the simulations, so I can probably give you the paper or a reference to the paper where they do the parameter estimation for why this is a binary black hole of this magnitude, but you're asking the wrong person.
Okay, maybe the last question. So is this method good for any observation about the black material, because that's the big hole still? not a black hole, a black hole in the science, as far as I know.
So let me repeat your question. So is this a method good to detect dark matter, is what you were asking? Very good question. The problem with dark matter is, and even worse, dark energy. I mean, we know something like 1% of the material in the universe. 10% of the order are dark matter, and 90% are dark energy. And the dark prefix says you can't see it. So the problem is, what is it? There's been a couple of recent observations basically with technically dark matter could be big blobs of matter, meaning stars that are not ignited, suns. So that might explain something of this. But there's also theories about baryonic matter that have slightly different material properties. Will this show dark matter? It will verify models, and so you will actually see, especially once we get observations together with optical and radio astronomy about delays and dispersion of space, and it will probably give you ideas if our models are correct. So far, the gravitational wave shows us that as far as we can observe it, the general relativity model is correct. But that's a small, not all-inclusive model in a way. It just predicts the stuff that we're used to see. And there's a couple missing parameters. And so we find actually confirmation for those. Yeah, again, this is kind of the second holy grail. The first one is the quantization of gravitation, and the other one is what is dark energy.
I'm joking now, so this is a perspective for the second Nobel Prize in the future.
Okay, let's thank the presenter one more time. Thank you very much.
All right. All right.